Welcome viewers once again to my YouTube channel. Once again, I want to bring you something very interesting, okay? And today we'll be looking at Zener Diodes. Isn't that interesting? Okay, you really need to know how to use them, what they are, why do we need them in a circuit, and how do we apply them in different circuits, okay? As a circuit designer, it will be good for you to also know how to, use them combined with resistors for you to be able to have the circuit work effectively. All right, so sit back, relax, pick up a piece of paper and a pen, of course, and join me. Let's do this together. All right, welcome back. It's very exciting for me to be showing you this because it used to be very confusing, and I hope you learn something from this. Okay, so just follow closely. You're going to get what I'm trying to show you here. All right, now we have a number of them. This is how they look. Okay, Zener diodes generally look like this, but I'll quickly mention something. There is one of them known as the 4148. I don't think you'll be able to see the number, but if you want to be sure of the number written on it, you could just get a magnifying lens like this and then put it under to be sure of the number written on it. Okay, now this one is actually a 4148. It's not particularly a Zener diode. Okay, 4148 is more like a PN junction diode, just something like this. But obviously, this can handle way more current than this. And then the difference between the two of them is the material they were made of. This is silicon, and I think this is germanium. I think I'm not very sure of that now, but the material they were made of. And then apart from that, they could do the same thing, just that the application of 4148 is we use them in a circuit where you have high switching frequency. Okay, we don't apply 1N4007. That's the number for this one. This is a PN junction diode. We don't use them in a circuit where you expect high frequency switching. Okay, but we make use of 4148 wherever you have high frequency switching. Okay, that said, because I really needed to point this out, they usually look alike. Okay, so check it and be sure that the number written on it is 4148 for you to know the difference. Okay, now Zener diodes generally are used to keep voltages. Their major use is to keep voltages at a particular point. They clip voltages at a particular point. All right, now if you put them in a circuit, what they will do for you is that if you have a higher voltage coming into that part of the circuit and you need a particular voltage to come out to feed another part of a circuit, you make use of Zener diodes. Okay, now the Zener diodes will help you to keep it at a particular voltage regardless of the amount of or the voltage coming at the input side. And generally their circuit symbol is this. Okay, you see something like a Z at the top. Meanwhile, for this normal PN junction diodes, you have them look this way. Okay, you see that the difference is you see something like this symbol. This tells you that this is a Zener diode and this is your normal PN junction diode. But like I said, we're looking at this, so let's just see. One way you arrange this in a circuit is just simply adding a resistor this way and then something like this. All right, now if you arrange it this way, a particular voltage enters at this point, and then depending on the Zener voltage, they are called Zener voltage. Okay, depending on the Zener voltage, you have a particular voltage coming out regardless of what's happening to the voltage here. I'm going to show you that in a bit on my breadboard, but how do we know the resistance you use here? Okay, now the resistance you use here depends on the voltage coming into that Zener circuit. All right, now the first thing you need to ask yourself is this: the Zener diode, how many watts is it? This particular one I have here is a 1/4 watt Zener diode. 1/4 watt Zener diode. Okay, and 1/4 simply means 0.25 watts, right? And we know that power is what? IV. So if it is 0.25 watts, then how much current can this Zener diode handle times the Zener voltage? So now I'm going to be using maybe a 5-volt Zener diode as an example. Okay, now let's pick 5 volts, for example, times 5. So the current that guy can handle would be what? 0.25 divided by 5. What would that give us? Where's my calculator? Okay, so we get 0.25 divided by 5. That gives me the current would be 0.05 amps, which is 50 milliamps. All right. So now we know that we need to limit whatever current entering into this Zener diode to 50 milliamps. Else, we're going to damage the Zener diode. Okay. Now, where does this come in? We need this for us to be able to know the resistance value we'll be using here. Now, let's assume we want to feed this 5-volt Zener, at the input side. We want to feed it with maybe a 12-volt input. All right. So we know that V is IR, a very, very beautiful formula. May God bless. What's his name again, sir? This guy, what's his name? Ohm. This is Ohm's law. Okay. So V equal to IR. Now we take 12. Follow this, minus the Zener voltage 5 is equal to the current. We want to limit it to 50 milliamps. But remember, now the Zener diode will be sharing a particular current with the component, or the component or whatever we'll be putting at the output. Okay, there will be a load here. All right, so we'll take that load into consideration. So we're assuming that 50 milliamps is the maximum that this guy can take. But remember, when it is loaded, okay, when it is loaded, the Zener diode and the load will share whatever current we are putting into consideration. So let's take let's say we are giving it 50. All right, 50. That's current times which resistance do we use? Now I'm using 50 because assume it is not loaded. The Zener diode can still be able to keep handling this amount of current for a while. Okay, but when it is loaded, the load and the Zener diode would share this current, which is okay. So let's move ahead. Now 12 minus 5 gives me 7 equal to 50R. So our R here, our resistance here would be, 50 is in, this is, this is 7. Let's take this all out. It is 12 minus 5 equal to 50 milliamps over 1000, okay, times R. Now let's do all our whatever. 12 minus this is 7 times 1000. 7000 equal to 50 R, where R will be what? 7000 divided by 50. What would that give us? 7000 divided by 50. That gives us approximately 140 ohms. All right. So if we're putting in 12 volts here, 12 volts here, we want to make this resistor value to be minimum, okay, greater than or equal to what? 140 ohms. Okay, so we can have 5 volts at the output. Now remember, let me just state this. If I put a resistor higher than this 140 ohms, it's still going to work fine, but take note that it will reduce the amount of current the load would have. Okay, and of course, increasing it also increases the safety margin, meaning that as I increase this, if the voltage keeps increasing, the Zener diode is still, within safe limits. All right. So let's check out this on the breadboard and see the result of what that gives. Now this on the breadboard, I already have a 5-volt Zener diode here. Okay. and this is a 1K resistor. Now, what I would do is, from my variable voltage source, okay, I'm going to, well, this is my variable voltage source made from your normal laptop adapters. Uh, on request, I could teach you how to make this, all right? As an engineer or as a circuit designer, you need a variable voltage source, trust me. Okay, this is about 16 volts entering into this arrangement. Now, let's see how many volts we have across the Zener diode terminals. We see that it keeps it at what? 5.1 volts. Even though we have 16 volts entry, what we have at its terminal is what? 5.15. So it clips it at that voltage. All right. Now, how do you know what's entering? Look at what is entering: 16 volts. Okay. And what is coming out is what? 5.1. Let's replace this with another one, maybe a 12-volt Zener diode, and see how it clamps it. Let's put it here. Here. Okay. So let's see. 16 volt entering, and this is 12 volt output. Okay. So because this is a 12-volt Zener diode. Now let's increase the input to maybe around 26 and see what still happens. 12 volts. Okay. Input 26, and what you get at the output is what? 12, around 12 volts. So you see that it clips it at a particular voltage regardless of what is entering. But the last thing I would like to mention is, now, for the kind of the power rating of the resistor you use, okay, it's called, this resistor is called the current limiting resistor. Now, how much power, or what power rating do you use for this particular resistor? Already we know that P is current square times what? Resistance. All right. Now, we know the current we are permitting to flow into that circuit from this example. So let's see. P would be what? The current is 50 over 1000. Remember, it's milliamps, all squared, times what resistance value did we calculate for? We calculated for 140 ohms. 40 ohms. So let's calculate, let's multiply this. This would give us the power rating of the resistor we use. Remember, resistors have different power ratings. These ones I'm using for the example is, this is a half-watt resistor. There are many other resistors with different power ratings. Let me give you another, let me show you one so you can be able to understand what I'm saying. Like, for example, this is another resistor, but this is a 10 watts resistor. Okay, so as the voltage increases, you should be able to tell the power rating of the kind of resistor, the power rating of the resistor you'll be using to limit this current. So let's check. 50 milliamps, that's about saying this is 0 0.05. 0.05 times 0.05 gives me that, then multiplied by 140. So you see that we have our power to be approximately 0.35 watts. Now this is the power rating, minimum power rating you should use, which is, you know, close to what we used here. Now this is making sense because as you increase the resistance, the power rating could also be reduced. Okay, the power rating could also be reduced. Now this is half watt, and then we're having roughly like 26 volts entering, and what we have at the output is around 12 volts. Let's drop it a little bit, flips it to around 12 volts. Okay, now why did we have a higher voltage there, about 13? The reason is, well, remember, it's even still around 12 volts, even with a 29 volt input. Now, the reason why we have that higher voltage is there is no load at the output. Once we load the output, the voltage will still remain around that figure. Let's try to load it and see. uh, let's see. Okay, let me just use this as an example. Let's load it. This is a load now at the output. Just an LED, for example. Now, let's see what voltage we would have. Around 13, and that's because an LED is just a small load. Okay, but remember, what we had before the LED was introduced was higher than 13, about 13.16. But with the LED connected, it drops. You see that 13.15. Yeah, the LED will just draw a little current. But this should give you a general overview of how your Zener diodes work, okay? And you could use them in different parts of your circuits to be able to clip your voltages at a particular point, regardless of what's happening at the input side. Hope you learned something. And just in case you've not subscribed, kindly hit the subscribe button to encourage us to do more of this awesome content. Thank you very much, and see you next time. Feel free to ask your questions in the comment section. And if there's any video requests you would like me to do, kindly let me know in the comment section. Thank you, and see you next time.